Welcome back, everyone. We're diving into something pretty cool today. Speech synthesis. We're going to unpack a recent research paper detailing CosyVoice 2. It's a new speech synthesis model from the Alibaba Group. And you can find the full paper online, of course, but we'll break it down for you right here.
Yeah. It's a really interesting paper. It definitely tackles a tough challenge in the field. It's all about streaming synthesis, where latency is a major issue.
Latency. Always a pain.
Yeah.
Especially when you're talking about real-time applications.
Right. Exactly. CosyVoice 2 is designed with those applications in mind. Like, think voice chat, but with large language models.
Whoa. Okay, so we're talking about making LLMs more interactive. Super hot topic right now.
Yeah.
How does CosyVoice 2 even approach that? What's the underlying architecture?
Well, the model kind of separates things. It separates the meaning of the speech, the semantic information from the acoustic features, like tone and pronunciation.
So it's treating those two aspects separately. Clever, but how?
They have two main components to do this: a text speech language model, or LM for short, and a flow matching model. The LM takes text, regular text, and turns it into these abstract representations. We call them semantic speech tokens. They capture, like, the linguistic essence of the speech, but not the actual sound of it yet.
Gotcha. So it's like building a conceptual framework first before you add the sonic details. That's clever.
Exactly. And then the flow matching model comes in. It takes those tokens and adds in all those acoustic features: speaker characteristics, emotion, even accent.
So it's adding the paint to the canvas based on the LM sketch. Love that analogy.
Yeah.
So where does the actual audio come from then?
Right. So at the very end of the process, you have a vocoder. It takes all those acoustic features and turns them into, well, sound waves, the actual audio waveform.
Okay, makes sense. Now, one thing that jumped out at me in the paper was the use of, well, a pre-trained large language model. They used Quinn 2.50.5b specifically as the backbone for their text-speech LM. That seems different from how most TTS models work.
Oh, absolutely. It is. Instead of training a language model from scratch, they just took an existing LLM and used it. Streamlines the whole architecture. Lets the model focus on the speech synthesis part.
Efficient. I like it. They also mentioned something about handling multilingual input, something about masking out multi-character tokens.
Right. It's a neat trick. Think about, say, Chinese text. One token might represent multiple characters. If you try to pronounce that token directly, it sounds, well, weird.
Yeah, I can imagine.
So what they do is they mask out those multi-character tokens and force the model to, like, encode each character separately.
Makes sense. So it's like breaking down a complex word into its phonetic components, right?
Yes, exactly. And that significantly improves pronunciation accuracy.
Very cool. The paper also talks about something called finite scalar quantization, FSQ. They use it in the speech tokenizer. How's that different from regular vector quantization?
Traditional vector quantization, or VQ, basically maps speech segments to these fixed points. In a codebook, FSQ is more fine-grained. It quantizes each dimension individually. Imagine a higher resolution image. You get more detail.
Ah, okay. More information packed in. And what's the benefit of that?
Well, with FSQ, you get this zero-shot capability for other languages. Even though they only train the model on Chinese and English data, it can handle Japanese and Korean too.
Wow. That's remarkable. A single model handling multiple languages that accurately.
It's amazing.
Amazing. Okay, let's shift gears a bit. Let's talk about the flow matching model, specifically that chunk-aware causal flow matching model. That's what gives the system its streaming capability, right?
Yeah, that's the one. So the flow matching model takes those semantic tokens, the ones from the LM, and decodes them into a MEL spectrogram. A MEL spectrogram is basically a visual representation of sound frequencies over time.
Visualizing sound. Interesting.
And to capture the unique characteristics of the speaker's voice, they use what we call speaker embeddings. They also use reference speech to help the model mimic specific styles or emotions.
Okay, that makes sense. So it's like the blueprint from the LM plus some personalized touches. But how does it all come together for streaming synthesis with minimal delay? That seems tricky.
Right. The key here is this idea of a probability density path. It basically defines the distribution of that target MEL spectrogram using something called optimal transport flow. Imagine you're sculpting. You have a lump of clay, and you want to shape it into something specific. Optimal transport flow figures out the most efficient way to, like, move each bit of clay to get to that final shape.
Ah, okay. So in this case, it's about efficiently mapping the acoustic information to create the right sound.
Precisely. And the paper goes into some pretty deep math behind optimal transport flow.
Oh, I bet. Can you give us the gist of it?
Well, at its core, the optimal transport problem is about finding the most cost-effective way to move, like, mass from one distribution to another. In our case, the mass is that acoustic information, and the cost is basically a function of the distance between the source and target distributions.
I see. So it's not just generating the entire spectrogram all at once, but figuring out the best way to build it piece by piece.
Exactly. And the flow matching model uses this thing called a causal convolutional transformer unit to find this optimal transport plan, ensuring that the MEL spectrogram it creates is a close match to what we want.
Okay, cool. So that's how it works in theory. But how does it translate to actual streaming synthesis?
Well, during training, they use masks, different types of masks, to control how much of the input sequence the model can see at any given time.
Ah, so the masks are like blinders, controlling the model's vision.
In a way, yeah. They use 4 different types of masks: non-causal, full causal, chunk M, and chunk 2M. The non-causal mask lets the model see the whole sequence. The full causal mask, though, only lets it see past information, which is crucial for real time, right? And the chunk M and chunk 2M masks, they're kind of middle ground. They let the model peek ahead a little bit.
So it's like training the model to be versatile, to adapt to different situations depending on how strict the latency requirements are. But why train on all these different masks? What's the benefit?
Well, that versatility is key. In applications where latency is absolutely critical, you can use that full causal mask, and the model can actually start generating speech before it even has all the text.
Whoa, hold on. It's like the model is thinking on its feet, generating speech on the fly.
Pretty much.
That's wild. But doesn't generating speech in chunks like that, compromise the quality?
That's a fair point. But what's amazing is the paper shows CosyVoice 2 achieves near human parity in both streaming and non-streaming modes, so the quality is pretty much indistinguishable from human speech, even in real time.
Okay, now that is impressive. Fast AD high quality. But speech is more than just words, right? There's style, emotion, even dialect. How does CosyVoice 2 deal with all that?
That's where instructed generation comes in. CosyVoice 2 was trained on this massive data set, but it wasn't just text and speech, it had all sorts of instructions too.
Instructions, like what?
Oh, all kinds. Simple emotional cues like speak with a happy voice, to more complex things like imitate a British accent, like giving the model a director's cue card, basically.
Uh-huh. I love that analogy, guiding the performance. Are there any specific examples of these instructions? I'm curious now.
Definitely. Table 1 in the paper, it's a goldmine of examples. You can instruct the model to change the speaking rate, add vocal bursts like laughter, switch between dialects, even emphasize certain words or phrases. Pretty remarkable control, actually. It really opens up the possibilities, doesn't it?
It does. You can create synthetic voices that are not just accurate, but also incredibly expressive and nuanced. That's amazing. But let's get back to the nitty-gritty. How does CosyVoice 2 handle multiple speakers? And how do they avoid that catastrophic forgetting issue when it learns new voices?
They use a technique called multi-speaker fine-tuning, or MSFT for short. Basically, instead of training on just one voice, they use many voices simultaneously, like an actor learning to play different roles.
Ah, a vocal chameleon. That's cool. But how do they keep those voices from getting mixed up?
They use speaker prompt tags, little labels added to the input text, speaker A, speaker B, things like that. So the model knows which voice to use for each utterance.
Smart. So each voice gets its own unique identifier. Now, the paper also mentions reinforcement learning. Used to refine this whole fine-tuning process. What's that all about?
Yeah, reinforcement learning is all about optimization, making the model perform better during this fine-tuning stage. They use 2 metrics as their reward functions: speaker similarity, or SS, and recognition word error rate, WER. The goal is to, well, maximize that speaker similarity, make sure the synthesized speech sounds like the target speaker, and at the same time minimize those word errors, keep the pronunciation clear and understandable.
It's like giving the model feedback. Reward it when it gets the voice and pronunciation right, and nudge it when it makes a mistake.
Exactly. And this feedback loop helps the model learn and improve over time.
Makes sense. You mentioned earlier that CosyVoice 2 does better in Korean than Japanese. Why is that?
That's an interesting observation from the paper. It all comes down to the writing systems. Japanese and Chinese share some characters. So sometimes the model ends up pronouncing Japanese words with a Chinese pronunciation, like it's accidentally applying the rules of one language to another.
Ah, I see. The shared characters trip it up. So languages with totally distinct writing systems might be easier for the model to handle.
Potentially, yes. The less overlap, the less chance of confusion. But the researchers also point out that the amount of training data matters a lot. They think that more Japanese training data could close that performance gap. It really emphasizes how important data diversity and volume are, especially when you're training these multilingual models.
Data is king, as they say. All right, let's dive into the performance evaluations. How did CosyVoice 2 stack up against other state-of-the-art models?
They ran a bunch of tests on benchmark datasets, compared CosyVoice 2 to both open source and closed source models. On one dataset, a subset of the LibreSpeech corpus, it actually outperformed all the other models. Achieved state-of-the-art results in content consistency, speech quality, and speaker similarity.
Setting a new standard? Impressive. Anything else stand out?
Here's the kicker. On some metrics, the model actually did better than humans.
Wait, what? It outperformed human speakers?
Yeah. Pretty wild, right? It suggests that CosyVoice 2 is reaching a level of naturalness that's almost indistinguishable from real human speech. They also tested it on the seed datasets, which are more challenging, wider range of domains and speaking styles. And again, CosyVoice 2 performed really well.
Wow. Achieving near human parity is a huge milestone in speech synthesis. Any surprises during the evaluations?
One interesting thing they found was some inconsistencies in the speaker similarity scores, depending on which speaker verification model they used.
Ah, so the way you measure speaker similarity can affect the result.
Exactly. It highlights the need for a more standardized approach to evaluating speaker similarity in TTS models. Otherwise, it's hard to compare apples to apples, you know?
Definitely. You need a common scale to make a fair assessment. Now, the researchers also did a modular ablation study to figure out how much each component contributes to the model's performance. Can you walk us through that?
Yeah, the ablation study was basically like dissecting the model. They started with a basic model similar to the previous version of CosyVoice, and then they added the new features one by one. LLM initialization, removing speaker embedding, using FSQ. By comparing performance at each step, they could see how each modification impacted the model.
It's like reverse engineering the model to see how each piece contributes to the whole. What were the key findings?
Each modification led to noticeable improvements in both content consistency and overall performance. For example, using a pre-trained LLM as the backbone of the text-speech LM led to a significant reduction in content errors. Shows how powerful those pre-trained models are.
Makes sense. You're giving the model a head start in understanding language.
Yeah.
What about removing the speaker embedding from the LM? What effect did that have?
That one's interesting. Removing the speaker embedding actually helped the model generalize across different speakers. It seems that separating speaker information from the linguistic content made the model more flexible and adaptable.
So it's learning the what of speech first and the who later on. This modular approach seems to be a big part of why the model works so well. But beyond all the technical stuff, what are the real-world applications of a model like this?
Oh man, the possibilities are huge. Think about voice assistants, having a natural human-like conversation with your device, getting responses in real time with minimal lag, or personalized audiobooks. Imagine choosing different voices, accents, even emotional tones, all tailored to you.
That would be incredible. Truly personalized experiences.
And think about video games. Characters that respond to you in real time, adapting their speech to the situation. Or educational tools that tailor their explanations to different learning styles, speaking in a voice that's engaging and easy to understand.
It sounds like we're on the cusp of a new era in human-computer interaction. And models like CosyVoice 2 are leading the way. But with great power comes great responsibility, right? Did the researchers acknowledge any limitations of CosyVoice 2?
They did. They highlighted a few areas for future research and improvement.
Perfect. Well, let's dive into those limitations in our next segment, and maybe explore some of the ethical considerations surrounding this rapidly evolving field. It's fascinating to think about the potential, but also important to consider the limitations. So what were some of the areas they highlighted for future research?
One of the big ones is language support. Right now, CosyVoice 2 is mainly focused on a handful of languages, and like we saw with that Japanese-Chinese example, handling languages with those overlapping character sets can be tricky. Expanding the language coverage and improving how the model deals with those linguistic quirks is a natural next step.
Building a truly universal speech synthesis model that can handle the nuances of every human language. That's a grand challenge. What other limitations did they mention?
Well, another area for improvement is in controlling those really fine-grained acoustic features.
Well,
Through textual instructions, I mean. CosyVoice 2 is great at modifying things like speaking rate and emotion, but there are some aspects it can't quite manipulate yet, like timbre, the unique tonal quality of a voice, just from text alone.
So if you wanted to create a character with a very specific, distinctive voice, you'd still need more than just text. You'd need, like, reference speech or something.
Yeah, for now,
Yeah.
giving the model more direct control over timbre just from textual instructions, that would be a big leap forward.
I can see that. It would open up so many possibilities. Imagine describing a voice with words, and the model just nails it. Revolutionary for things like entertainment, virtual reality, all sorts of stuff. Any other limitations they pointed out?
They did briefly mention that CosyVoice 2 isn't really designed for singing.
Oh, interesting. Why is singing so much harder for these models?
Well, think about it. Singing involves way more complex melody and rhythm patterns than regular speech. The model needs a deeper understanding of musicality, being able to control pitch and timing with much more precision. Adapting models like CosyVoice 2 to handle those nuances of singing, that's a whole other ballgame.
It's a fascinating challenge, though. Imagine composing a song and then hearing it sung by a synthetic voice with all the realism and emotion of a human singer. That would really blur the lines between human and machine creativity. And as these models keep getting more sophisticated, it raises some big questions about the future of human-computer interaction and even the nature of creativity itself.
Absolutely. These advancements in speech synthesis are pushing the boundaries of what we thought possible. It's making us rethink how we define human creativity and how technology fits into our lives.
This deep dive into CosyVoice 2 has been really eye-opening. We're clearly on the verge of something big with speech technology, with implications for communication, entertainment, so many fields.
The applications are vast, and they just keep expanding as these models evolve. It's an exciting time to be working in this field.
For our listeners who want to dig deeper, where can they find out more about CosyVoice 2?
The full paper's on arxiv, and the authors have also put the code and the pre-trained models on GitHub. Lots of great resources to explore if you want to get into the technical nitty-gritty.
This has been a fantastic exploration of cutting-edge speech synthesis. CosyVoice 2 really shows how much progress has been made, and it feels like we're just scratching the surface of what's possible.
As these technologies continue to advance, they have the power to change how we interact with machines and with each other, opening up all these new possibilities for communication, creativity, human expression.
It's inspiring, to be honest. Thank you for joining us on this deep dive. And thank you to all our listeners for tuning in. We'll continue to explore the frontiers of AI, bring you insights into the latest breakthroughs and how they're impacting our world. Until next time, keep questioning, keep exploring, and keep pushing those boundaries of human knowledge. It's a good reminder that even with all this progress, there's still work to be done.
So what about those limitations? What were some of the specific things they called out for future research?
Well, one thing they pointed to was fine-grained control of acoustic features, like through text instructions. CosyVoice 2 is pretty good at changing things like speaking rate and emotion, but it can't really manipulate things like timbre.
Timbre.
Yeah, like the unique kind of tonal quality of voice, just from text, I mean.
Oh, I see. So if I wanted to create a character with a really specific, unique voice, I couldn't just describe it with words. I'd still need some other input, like a reference speech or something.
For now, yeah. Giving the model more direct control over timbre, just from text, that would be a pretty big step.
I can imagine. It would open up so many creative doors, especially for things like character creation in games or animation, where you really want unique and distinctive voices. Did they mention any other limitations?
They did touch on the fact that CosyVoice 2 isn't really built for singing.
Interesting. Why is singing such a challenge for these models?
Well, singing is just so much more complex, melodically and rhythmically,
Right.
compared to regular speech. You need a much deeper understanding of musicality, the ability to precisely control pitch and timing. Adapting models like CosyVoice 2 to handle all those nuances of singing, that's a whole different ballgame. It's a fascinating area, though. Imagine being able to compose a song and then instantly hear it sung by a synthetic voice with all the realism and emotion of a human singer. That would be mind-blowing.
Yeah.
As these models keep getting better, it really makes you think about the future of human-computer interaction and even the nature of creativity itself.
Totally. These advancements in speech synthesis are really forcing us to rethink things, how we define human creativity, how technology fits into our lives. The lines are definitely getting blurrier.
This deep dive into CosyVoice 2 has been amazing. It's clear that speech technology is about to go through a massive transformation. The implications for communication, entertainment, so many fields are just enormous.
No doubt. And
Right.
as these models keep evolving, who knows what we'll be capable of? It's an incredibly exciting time to be working in this field.
Well said. For our listeners who are eager to explore further, where can they learn more about CosyVoice 2?
The researchers have made the full paper available on arxiv, and they've also shared the code and the pre-trained models on GitHub. So if you're interested in the technical details, definitely check those out. Lots of great stuff in there.
Awesome. This has been a fantastic exploration of cutting-edge speech synthesis. CosyVoice 2 really shows us what's possible, and it feels like we're just at the beginning of this journey.
I agree. As these technologies continue to advance, they really have the power to change how we interact with machines and with each other, unlocking all sorts of new possibilities for communication, for creativity, for human expression. It's a pretty incredible time to be alive, wouldn't you say?
I couldn't agree more.
Nice.
Thanks for joining us on this deep dive. And to all our listeners, thank you for tuning in. We'll continue to explore the world of AI, bring you the latest breakthroughs, and discuss their impact on our world. Until next time, keep asking questions, keep exploring, and keep pushing the boundaries of human knowledge.